So the next thing I want to talk about is our work on kidney exchanges in this context. And this was led by Rachel Friedman, who was an undergraduate at Duke at the time and is now a PhD student at Berkeley in Stuart Russell's group, who we saw before. It's also joint work with Jana and Walter, who we've seen before, and also with John Dickerson, who I hope many of you know, and who is an assistant professor in CS at the University of Maryland, where he works primarily on kidney exchanges. So, his expertise was very valuable here. And here the idea is that we're going to apply these kind of ideas that we've talked about so far in the context of a kidney exchange. Now, I hope many of you already have some familiarity with what a kidney exchange is, but in case you don't, let's briefly go over it. So a kidney exchange is about organ donation. The kidneys that we have in our bodies filter waste from our blood, and so are necessary to life. And sometimes somebody's kidneys fail, in which case they would benefit from a kidney transplant. Where might you get a kidney transplant? Well, one way you might get one is from an organ donor who is deceased. Okay, if somebody dies, well, in a way that leaves their kidneys viable, you might get a kidney from that kind of person if they were an organ donor. Unfortunately, there are not enough of those kidneys available. Another way you might get a kidney is through a live donation, because human beings typically have two kidneys. They can donate one and still lead a healthy life with the other. So that's one way you might get a kidney, but then that requires finding somebody who is willing to give you a kidney. So maybe a very close friend or relative. Now, one thing that might happen is that you do find such a person, but it turns out you're not compatible medically. For example, due to blood type, right? Maybe you have blood type A, your willing donor has blood type B, and so your donor cannot give to you. You might think at that point, well, that's unfortunate, that's the end of it, but it turns out there's something else that can still be done. By the way, here is an article about the role of AI in organ donation, especially kidney exchange. This particular article talks a little bit about ethics as well, and that's why it discusses our work as well, which is focused on that. So what is this other thing that you can do? Well, you can exchange. So this picture illustrates that. So here we have on the left a mother who wants to give a kidney to her son, but they're not compatible, which is why that edge, that arrow is crossed out. And on the right-hand side, we see the same kind of thing with the husband who wants to donate to his wife. Also not compatible, but it turns out that the husband is compatible with the son on the left, and the mother on the left is compatible with the wife on the right. And so the two patients could simply swap their donors. Okay. And while it's illegal to buy and sell kidneys in most places in the world, and it's also illegal to give valuable consideration for kidneys, right? I cannot say, like, if you give my wife a kidney, I will give you a job. That is illegal. But swapping kidneys for kidneys is considered okay. So that's good. Okay, so what does it have to do with AI? Well, first, let's abstract a little bit more. So let's look at this picture here. What we've done is we've taken pairs like the mother and the son, right? So one person who wants to give on behalf of the other person and merge them into a vertex. So this vertex here on the left is donor one who wants to give on behalf of patient one, and they happen not to be compatible because their blood types are A and B respectively. That's the left vertex. And so here we actually have three vertices corresponding to three pairs of people. And the edges or arrows here indicate who can give to whom. Right? So donor one can give to patient two because they have the same blood type here. Okay. So that's the kind of situation that we're facing. So if you run a kidney exchange, you're going to generally get lots of pairs of people, and there will be lots of relationships in terms of who can give to whom. Right? And so that's the kind of picture you're going to face. And this is where AI has entered the picture because, or more generally, you could think of it as algorithms entering the picture, because at some point these graphs get so large, it becomes difficult for any human being to figure out what the best way is to match everybody together. Right? Let's say you want to maximize the number of people that got a kidney transplant. That actually turns out to be an NP-hard problem under some reasonable constraints on the problem. So it's an algorithms problem, it's an NP-hard problem, but algorithms developed in the AI community are able to scale to quite large numbers of patient-donor pairs and still solve them optimally. Here's another example. It's a little bit richer. So here it turns out we have 4 pairs. One thing you could do is you could take the 2 leftmost nodes here and have them swap with each other. But if you do that, nobody else can match. Another thing that you can do here is there's what's called a 3 cycle. If you look at the 3 nodes on the right, if you look, donor 2 could give the patient 4. Donor 4 could give the patient 3. And donor 3 in turn could give back to patient 2. And that way all 3 of those patients have received the kidney. So that's what we call a 3 cycle. So that's another thing that you could do, that here you would actually get 3 people matched. Okay, so first thing you might try to do is just maximize the number of people that receive a kidney. But now the question that we asked ourselves is, well, maybe we want to think about more than just the number. Even if you just wanted to break ties, right? Like if in the example that we now have on the slide with the 3 vertices, there's actually 2 optimal ways of doing it in terms of maximizing the number of people that get a kidney. You could do the 2 cycle on the left. You could say, oh, donor 1 gives the patient 2, donor 2 gives the patient 1. That's a cycle that would satisfy those 2 patients, and patient 3 would be left out. But of course, you could do the exact same thing on the right, match 2 and 3 together, and then patient 1 would be left out. So one approach is to say, well, those are equally good outcomes, and maybe we toss a coin. It's a little bit interesting how exactly you would toss a coin in the optimization procedure. Or maybe you say, well, it's going to be an accident of how somebody coded up the optimization algorithm, that which one actually gets the kidney. But we wanted to think about, well, what if you actually wanted to deliberately think about who should get the kidney in this case, between patient 1 and patient 3, let's say. And so I want to sketch a scenario for you where, so let me describe fictitiously who patient 1 and patient 3 might be. Imagine that patient 1 is a 20-year-old female Black student athlete who has this problem with her kidneys, but otherwise is completely healthy and has a wonderful life ahead of her. That's patient 1. Patient 3, by the way, there's going to be a Zoom poll, as you might expect, but just to warn you. Patient 3, let's say, is a 50-year-old white man with a drinking problem and a criminal record, but also with 3 children that depend on him. Okay, so that's your setup. And now what I want to ask you is, I'm not going to ask you which of the 2 you prefer or would like to see prioritized, but just whether you would, based on those kind of features that I just described, would you feel comfortable or would you feel like you should prioritize one patient over the other? Again, I'm not asking you which patient of the 2 you would prioritize, but whether you would be willing to prioritize patients on the basis of such concerns. So here are the options I gave in the poll. You might say, well, in this case, I would prioritize one over the other. And in fact, I would almost never choose to, let's say, toss a coin. Right? You would tend to have a clear idea over who you would want to prioritize. Of course, if the 2 patients were exactly identical, maybe then you would toss a coin. But in general, you would prioritize. Or a response might be, you would prioritize in this case, but in quite a few other cases, you would probably prefer to toss a coin. Or you might say you would toss a coin in this case, but you can imagine quite a few other cases where you would strictly prioritize. And finally, you could say, well, you would toss a coin pretty much always. Or you might say that you would object to this way of presenting the problem, which leaves the question of what kind of presentation you would like to see. Okay, I'll leave it open for a couple more seconds. And end the polling. So 2/3 of people said they would prioritize in this case that I just described, but quite a few other cases they would choose to toss a coin. And the remaining 1/3 said they would prioritize in this case and almost never toss a coin. Okay, so that's what happened for this particular audience. Answers to this question tend to vary across audiences, I'll say. Good. Okay, but so we're going to come back to this idea of tossing coins, but for now, put that aside. So what did we want to do? We wanted to do something like the moral machine that we saw before, where we ask subjects questions about who they would prioritize in certain situations. But we also wanted to avoid some of the problems, like I mentioned, that in the moral machine, there was the homeless person, which presumably is an attribute or a feature of the patients that we wouldn't even want to present. But we also didn't want to be the final arbiter of what should be presented and not. So actually, we did a first round with human subjects, actually from Mechanical Turk, where we just asked them open-endedly what they thought were features of patients that ought to be taken into account in terms of whether they are prioritized. And we also asked them what features are that ought not to be prioritized. But what you see here on this slide is features that generally people thought ought to be taken into account, though some maybe disagreed. So here what we saw is that there are a number of different, so people gave all kinds of responses, then, but we categorized those responses into categories. And so here, the most popular categories in terms of the ones that people felt ought to be taken into account were the patient's age, behavioral aspects of the patient's health, like whether they were a smoker or drinker maybe, and also other general aspects of their health, like whether they have other conditions. And those were the least controversial to take into account on the side where people felt they ought to be taken into account. And then there were some ones that were controversial, for example, whether the person has dependents, like children that depend on them. Should you take that into account when you prioritize patients, or whether they have a criminal record? Okay, and so this is kind of the top of the list. Of course, there's the bottom of the list. There were things that everybody agreed should not be taken into account, like race. Pretty much everybody actually felt that race should not be taken into account in this kind of context. So we went with the top 3 categories here that seemed to be the least controversial: age, behavioral aspects of health, and other aspects of health. And from that, we constructed some fictitious patient profiles. We didn't do this, we have not deployed this in reality at all. So just as a caveat, this is a proof of concept study where we came up with actually 8 patients that varied on these 3 attributes: age, behavioral aspects of health, and general aspects of health. And for each of these attributes, we had only 2 possible values in the study. Some fictitious patients were 30 years old and some were 70 years old. Okay, some rarely drank alcohol and some frequently drank alcohol, 5 drinks per day. Some had no other major health problems, and others, just to choose something concrete, we chose had skin cancer in remission. Okay, so those are 2 values for each of 3 attributes, so that gives you 8 combinations of possible patients. And then the next thing that we did is that we asked human subjects, again from Mechanical Turk, to compare pairs of them and say, well, which one of the 2 would you prioritize? Okay, of these 8 possibilities. So we would choose 2 of the 8 and ask a subject which of the 2 would they prioritize, not with the option of a coin toss at this point. And this is what we found. So in the second round, where we asked Mechanical Turkers to do those kind of judgments, here's how often each profile was preferred to another profile. So maybe unsurprisingly, the most popular profile was the young, rarely drinking, healthy patient that was preferred 94% of time to whatever other profile it was being compared with. Okay. By the way, so here we asked Mechanical Turkers because that was the easiest way for us to get a set of people to give responses. You can ask a good question about what actually would be the ideal set of people to ask these kind of queries from. So let's maybe save that one for the discussion, but I want to get that in your mind already. But here we just got people from Mechanical Turk. Okay, now what we needed to do is the algorithms that solve or that try to clear these kidney exchanges, try to figure out who to match with whom, they're very flexible in terms that they can deal with weights on the vertices, right? If a weight on the vertex indicates how important that vertex is, they can deal with that. In our study, actually, all we did was break ties. So we actually said, well, we're still going to maximize the number of people that get matched. But if there's a tie, we want to break that based on these profiles. So we need to put some weights on the vertices then. So how do we get from these responses to numbers? One way to do so is with what's known as the Bradley-Terry model, which is a statistical model that's intended to explain why one choice was made over the other. And what this model says is that each profile of a patient has a weight. And then the model imagines that the probability with which somebody will choose one profile over the other is proportional to the weight. That's how that model works. And then you can estimate those weights, and then you could use those in the solver. So that's what we did. Actually, there's two different ways that you might estimate these weights. So that's the two different columns here, depending on whether you think that it should be like a linear combination of weights based on the attributes, or you're willing to have any weight for any profile. So that would be the direct column. Let's focus on the direct column, right? So that you see that, like, estimating these weights gives you different numbers for the different profiles. Now, what I want to point out here is that these weights in some sense seem wrong, in the sense that you see here that the young, rarely drinking healthy patient has a weight that's more than 4 times the next profile. But now that doesn't mean that we think that the first profile is more than 4 times as important as the second profile. What it means is just that we're very confident that people generally tend to pick the first over the second, right? So that's potentially a problem. So I'm going to argue that it actually doesn't really matter a whole lot. It turns out the only thing that really matters here in experiments is the order in which you get the profiles, and I'll show that in a second. But generally, this is a good question, right? How should you get these weights? And this is related to a question that Chengwu asked before about, utilities really probably should reflect attitudes toward risks. And here we don't have any risks, we just have explicit comparisons. Okay, but let's see what actually happens. So now we did this, we said, well, we're going to try to maximize the number of people that are matched, but we're going to break ties according to these weights. And here's what happens. Okay, so here, let's look at this figure here on the right. The y-axis tells you how often somebody in a particular profile was matched across our simulation. So for kidney exchanges, there are good simulators, and that's what we use to get an idea. Again, we didn't use this in the real world. And so here we see all the different profiles on the x-axis, and they're ordered by their weight here, same order as here. And so what happens? So you see 2 kinds of boxes. The gray boxes are the standard algorithm, what we call the standard algorithm, that actually doesn't look at these profiles, right? That's just trying to maximize the number of matches. And so unsurprisingly, what you see here is that the fraction of times that a profile is matched doesn't really depend on which profile it is, which is not at all surprising. It's just a sanity check, because that algorithm isn't looking at the profile. It's not looking at whether somebody was young or rarely drinking or healthy or anything like that. But that's just the baseline. And we compare that to our algorithm, the prioritized one, that still maximizes the number of matches, but breaks ties by prioritization. Unsurprisingly, now the higher ranked or more prioritized profiles get matched more often. So that shouldn't be too surprising. But one thing that's maybe a little bit surprising is that the effect seems to level off towards the end. And you see that, like, if you look at the profiles on the right there, it doesn't seem to be really going down anymore. And there's a reason for that we'll explain in a second. First, I want to come back to this issue of the weights, that it seemed unreasonable to have like a 4 times as large weight on the most prioritized one over the second most prioritized one. But it turns out, like, any kind of monotone transformation you do to those weights, so anything that respects the order. But for example, here, what we did is we said, well, we're going to take the same order, but we're going to make the step size always the same in terms of how the weights come down. And if you use that instead, you still get basically the same picture, right? It's not clear that anything has really changed here in any significant way. So it seems to not really matter. And there's some intuition that we'll get for that in a second. Okay, so but now I want to get back to what is going on with this leveling out at the end. And here's what's going on. So if you, not necessarily considering this prioritizing, but if you think about, well, what is it actually that helps you get matched in this kind of, in a kidney exchange? It depends a lot, especially once the market gets large, right? So once you get enough people in your kidney exchange, the main determinant of whether somebody is going to get matched, or really whether a pair of a donor and a patient is going to get matched, depends primarily on their blood types and whether those blood types are easy to match. What does it mean to be easy to match? Well, a donor is easy to match if they're a universal donor blood type. A patient is easy to match if they're a universal recipient blood type. And so how easy the pair as a whole is to match depends on the blood type of both of them. And then there are different conditions that you might be in. The most difficult situation to be in is that you're an underdemanded pair, which, right, so in the large, you can make this distinction between the different kind of pairs, and some of them are going to be underdemanded in the market that we're not going to be able to match all of them. And that could be because, for example, you have a patient with a universal donor blood type or a donor with a universal recipient blood type, or both, or something like that. There are also pairs in the opposite condition that are over-demanded. We wish we had more. We would be able to match more people if only we had more of this kind of pair. And then there's some other conditions. You might be self-demanded, where actually the patient and the donor do have the same blood type, but they're incompatible for another reason. Or maybe they're not even incompatible. The exchanges really would like more pairs to come that are actually compatible with each other, but they might hope to find an even better match in the market. And then there's reciprocally demanded, which means one of them has blood type A, one of them has blood type B. It's not so much that one is easier or harder to match, but it's just that they don't fit together. And as the market gets large, most of the pairs are going to be okay. In particular, all the green conditions, so the last three conditions, they're generally going to be okay and get matched. It's the under-demanded pairs that we're generally not going to be able to match all of them of. And so that suggests that when we look at that picture that we had, the figure that we had before, where we saw things flattening out, this is the same figure, but we're only looking at the under-demanded pairs. So not the whole market anymore. Otherwise, the same kind of figure as the first one that we saw. Again, the standard algorithm doesn't look at the profiles, but now if you look at the prioritized algorithm, what do you see? Well, it has a huge effect here on the under-demanded pairs. And the idea is actually, like with hindsight, is fairly straightforward, right? That we can't match all of them. And so what's going to determine which ones of them are going to get matched is in large part what their profile is, right? And we're going to generally match the ones that are most prioritized, that have the most prioritized profile. So if you were in fact in an under-demanded situation, but your patient was young, rarely drinking, and otherwise healthy, you now have a really good chance of being matched. The cost of that is that once you go to the right, pretty quickly, like halfway through, the chance of getting matched drops to basically zero. Okay, and that's what's causing the flattening out, is that at some point you hit zero and you can't go any lower than zero, so it's flat from there on, right? So in this part of the market, you see this flattening out. Now in the aggregate market, that it doesn't flatten out at zero because there are people in the other conditions that are going to get matched anyway. But this is what's causing the flattening out. And something about that feels uncomfortable as well, right? That's now by doing this prioritization, you've basically said that some pairs are effectively never going to get matched in this exchange. So that's kind of an interesting high-level takeaway. So let's talk a little bit more about that in a little bit. But that was our first study on this. Any quick questions that anybody has? Just want to make sure. Okay. So based on these kind of ideas, now there's a lot of interesting research in a lot of different directions that you can do. So I want to briefly illustrate some of the follow-up work we've done, just to illustrate what different directions you can take. So one way that you can go is you can go into theory and machine learning theory, which my amazing student Hanrui Zhang has been doing, to think about questions like, so suppose that we have this kind of setup like we did, where we go online and we ask mechanical Turkers for feedback, or you set up a website like the Moral Machine team did and collect data from subjects that way. You might like to ask, first of all, how many subjects do you really need to ask questions from? And how many queries do you need to ask of each of them before you can be pretty confident that you have the right idea? Okay. And this is going to come back to the point that I raised earlier, where we said, well, do we really want to do this simple thing of building a model of every voter and then having those models vote straightforwardly, or do we want to think about something that's a little bit richer than that? So before we get to that, let's first think about what our eventual data will look like. So these rows here are our data points. So a data point is an answer to a query. And so, for example, here, the first row means, well, the first column is the agent. Agent here really means human subject in this context, right? So the human subject that answered this particular query was Alice. The X's describe features of the comparison that was presented to Alice, right? So, so like the ages of the patient and so on. So here, just for specificity, I said, well, like, let's say X1 is 1 if the patient on the left were younger. In reality, you probably want to know the exact numbers, but just to illustrate. And X2 is some other feature of the comparison and so on. And then Y is the label that Alice gave, meaning, for example, 1 might mean that Alice that said that the patient on the left is the one that ought to be preferred. Okay. And so that's our setup. And our goal now is to be able to predict the Y column based on the X's and maybe the agent. Well, so that's the question, right? So in the end, we want to make decisions based on just the X values, right? We want to somehow aggregate across the different agents. But what should we model? Well, one thing that you could try to do is you could first try to model every individual, right? And so here, like from a machine learning perspective, you need to have some concept or hypothesis class. So let's say here we want conjunctions. It doesn't really matter, right? But basically you could see, well, one way to model Alice here is that she will say that the answer is 1 as long as X1 is 1, right? That's her, or that's one hypothesis that explains her data. Others do too. For Bob, our hypothesis might be that like if X1 and if X1 and X3 are both true or both 1, then Bob will say 1 as the label, right? That actually fits all of Bob's data. And Charlie, we could model just by saying, well, Charlie just looks at X2. So that's one way you might proceed. And so we can actually, fit every individual's data for this particular set of data perfectly. Alternatively, you might say, no, we're going to just ignore which agent said what. We're just going to look at we're just going to erase that column completely, and we're just going to look at the X's and the Y's. This is actually what we did in the first kidney exchange study. We ignored what human subject each response came from. And one way you could do that is, it turns out that like probably the best way to model this data, if you weren't going to look at the individual agents, is say just X1 is what predicts whether Y is going to be 1 or 0. It doesn't predict it perfectly like this first row for Bob, but it's pretty close. So what is the right thing to do? And it feels like kind of both are falling short, right? It doesn't seem that we should just ignore entirely who said what, as the second thing does. But also it seems easy to be too confident about our model for one individual agent, right? Like, is Alice really just looking at X1, or is she even looking at X1 at all, or is she always just saying 1 anyway? That's not really clear here. And so we wanted to think about what's kind of a more sensible way to model all this, right? Is there some kind of comfortable intermediate interpretation where it's not like we're going to make models of individuals and then completely treat those models of individuals as truth, but at the same time, we do still think about the fact that different data came from different individuals. And so here's the model that we settled on, that we imagine that there is a correct concept that we wish to learn. If you want to, this is kind of a form of moral realism, though just for practical purposes, where we think that there is a correct way of saying which is the right, let's say, patient to prioritize. And then we assume that our subjects, our human subjects that we're asking queries from, they have their own concepts in mind for what the right thing to do is, and they answer according to those, but they're kind of noisy versions of the correct version. So they make some mistakes, right? Like I said before, like maybe I have some moral failings that I make the wrong decision in some cases. And so everybody has some moral mistakes that they make that way, but they're different. And so there's some noisy process that generates this, right? This picture actually formally is supposed to be a Bayesian network, if you're familiar with those. And then we imagine that now examples come by, right? So it's a particular queries that we ask, defined by their X values, and those together with some particular concept that some individual subject has determines what label that subject gives to that particular example. Okay, So this is kind of our mathematical model graphically of what is happening in this whole context, right? And so when you have this model specified, now you can actually think about estimating C star, right? That's really what we want. We want to figure out what is the truly correct concept that we never see, but we want to estimate what the real moral truth is, right? Of course, whether there is such a thing as whether moral realism is correct, that's a philosophical question. But you could think of it as here we just pretend that it is and proceed accordingly. Okay. And once you've set up that whole model, now you can prove formal results. So here is an example of a theorem. I'm not going to talk you through the details of this theorem, but just to look at what kind of thing what's going on here is that it's, if you imagine that you have some class of concepts or hypotheses that you would consider, and some assumptions over the distribution and some assumptions over what the noise looks like in terms of how people make mistakes relative to the correct concept, then given all that, you can now prove theorems about how many different agents you need and how many data points in total or per agent you need in order to be able to output the correct concept with high probability. And so this is a result in pack learning theory, but very much motivated by this kind of setup. So that's one kind of thing you can do. You can go in this theory direction. You can also go into the direction of more behavioral research. And that's what we did in this paper. So even more co-authors. So Lak Chan is a postdoc working with us who got his PhD in philosophy at Duke. Kenzie was a post-bac researcher who is now doing her PhD in psychology at Oregon. And Duncan McElfresh is one of John Dickerson's PhD students. Yes, so we're in computer science. And so in this paper, what we were concerned about is that, so everything I told you about so far takes human subjects' responses as accurate of what their real beliefs are. But presumably there are all kinds of behavioral biases, and the way that you ask queries is going to influence what responses they give. And what we were worried about in particular, and there was some evidence that this might happen in the psychology literature, is that they would form a belief of what the AI system that's trying to predict what they're going to answer, right? And that's also choosing the questions to ask them, what they're going to form beliefs about what that system thinks about them, and then try to match, in some sense, those beliefs. Okay, that's a little bit of a complicated story, but so what we did was we said, well, we gave them some fake feedback that said that based on some earlier responses that they gave, we said, well, according to our AI, you care relatively more about the life expectancy as one feature, right, than about how many dependents they have. Those were variables here in what they were being asked about. And this feedback, in fact, was random. Right? It wasn't actually based on data that we'd seen before. It was just we tossed a coin about what feedback they would receive so that we could study what effect getting this feedback had on how they responded to future queries. And in some sense, you would like there not to be an effect, because if there's no effect, then you can maybe take the data more at face value. It looks like, so it's kind of on the borderline of whether this is significant, whether there's an effect, right? So it's close to 0.05 p-value. But it does seem that it's going in the direction that we were worried about, that if you tell people that they care about life expectancy, it seems that they start to respond in a way that does actually value life expectancy more, right? And we'd like that not to happen. We'd like them to have their own idea about how much you should value it and respond accordingly. But it turns out they're sensitive to feedback, and they actually start to kind of match that feedback to some degree. I see there is a question here, right? So how big was the effect? So in what sense? So here you could see what percentage they went for life. And okay, good. I think it's clear. Good, right. And so here also you see the p-value. So again, it's on the border of significance. Interestingly, so just in a follow-up study, we also we did the same thing, except we changed the wording a little bit, and we said instead of according to AI, we said, well, according to expert psychologists, you care, based on your early responses, more about how many, or about the life expectancy. I'm not sure exactly how the subjects imagined this to be taken, like, did they imagine that there was actually a human being sitting there on the other side? But whatever they imagined, the effect of this was far larger, right? So people really seem to incorporate what they think expert psychologists think about them, much more so than the AI in this study. So not entirely sure exactly what to take away from this, other than this is probably still a reasonable cause for concern. One more that I want to point out was now we're actually going to get to coin tossing. So other than the poll that we did earlier, none of this involved any coin tossing, right? You had to pick either left or right. And we were also kind of worried about that because, as you saw from the poll that we did, in fact, people sometimes don't feel comfortable making this kind of comparison, right? And so in this study, we actually allowed them, right? So we presented them with patient pairs in this kind of a way that you see here on the top. There's patient A, patient B. We tell them something about how much they were drinking, how old they were, how many children they had that dependent on them. And now, besides just choosing one patient over the other, we also gave them the option to toss a coin. Okay, that was the new setup. And now the interesting thing is, right, we felt like we should add something like this because sometimes people do want to toss a coin. If we don't give that option, one risk is that some people just don't even want to participate in this whole thing, and so we get a biased sample. But also it seems to reflect something about how people feel, so we would want to model that. That being said, it turns out people toss coins for different reasons. Some people toss coins because, like, if the patients are kind of close to each other, right? Like one patient is 67 years old, the other patient is 68 years old. That's such a small difference. We don't want to like choose one over the other. We're going to toss a coin in that case. Some subjects are like that. Whereas other subjects toss coins more in situations where it's difficult to compare them because one feature kind of points in one direction and the other in the other direction, right? For example, this one patient is younger, but also is much more of a heavy drinker. And that might be the case where they toss coins. So there's a lot of interesting modeling here you can do in terms of figuring out what makes people toss coins and how you should integrate that back into the actual solver in the end. Great. Okay, so I want to close today by saying that on this part of the tutorial, there are many open research directions, right? It's really a very interdisciplinary topic, I think, that cuts across, of course, kind of machine learning and statistics and eliciting people's preferences, as well as ethics and philosophy, the behavioral sciences, and computational social choice for figuring out how to aggregate the different responses. Here are some specific directions I think are exciting to pursue. One is related to what we saw before with the kidney exchange, right? I said at the end that something about this higher level behavior that results, where we basically condemn some pairs to have zero chance of being matched in the exchange, seems uncomfortable. But we never really asked subjects directly about that kind of global property of the market, right? We only asked them about these local comparisons, like what about this patient versus that patient? Whereas maybe they actually would have views on what should happen globally in the market as a whole. And how would you be able to ask them about that? That's one interesting question. Another one that we've been interested in is using these kind of techniques not to make decisions in AI systems, but actually to help people and to give them feedback about how they're doing their moral reasoning so that it might become better, right? So you could think maybe of this as kind of an app that you would have on your phone that helps guide you, or like if you make some decision that doesn't seem consistent with its model of you, maybe it would actually kind of push you on it and like try to figure out why did you say that, whether you really made the right decision, but also maybe to learn from you again. So to really think about that kind of interaction with people. And then finally, maybe one of the most difficult ones is like, what if you actually wanted to do this for something like self-driving cars, right? I think we probably all agree that the way the moral machines is set up is maybe not exactly right for that, and that also wasn't its intent. The tricky thing there is now we really have to think about AI perception, right? That the car perceives the world and judges it that way. Like it has to somehow figure out, is that a person on the road or not? Excuse me. And so I think it would be really interesting to think about how you would integrate that. But I also think it's very difficult, and how difficult that is, I think, is well illustrated by, you may be aware of this problem that Google had, where it started labeling images of human beings as gorillas. And that was problematic enough. But the really surprising in some sense and difficult thing there is that it's really hard to fix that, because most of these things are being done using deep learning, and it's very difficult to just somehow just quickly correct the classifier to not do that, or to even give kind of clear feedback about what kind of things it's supposed to do and what kind of things it's not supposed to do. And so it's really difficult to fix. Of course, you can just remove the label gorillas, and it appears that that's what Google did. But that's obviously not it's just kind of a hack. How do you do that in the right way? And that's closely related to, it's not the same, but it's closely related to these kind of issues, that it's very difficult to get to be able to think directly about how we value these different classifications and maybe being able to make corrections to those. So that's, I think, why this is challenging. Good. Okay, I think this is a really good stopping point for the first half of the tutorial. We're actually slightly